screen. So since several of you were not there in yesterday's additional class, so I may just repeat what we are doing and then we will carry it on from there. And for others, it's I guess for them it's a revision. So we discussed that in statistics, we basically focus on two aspects. One is parameter estimation and another is decision making. For parameter estimation, we used one technique, what we call as the maximum likelihood estimator. And that technique tells you how to infer population parameter, which is unknown, from the sample which is given to you. So what combination of the sample should you use in order to arrive at the population parameter? And that is what was done for Poisson and exponential distribution. In your homework, I gave it for the Gaussian distribution. Okay. The other aspect of the statistics will be highlighted through this portion, which we call as the decision making or hypothesis testing. And in order to give you an idea of what it is about, I framed a question and we will try to understand the working of hypothesis testing through this question. So the question reads as, a company claims to manufacture power banks with mean output of 10 watt. The standard deviation somehow of 1 watt is given. To check the claim, 20 power banks were randomly selected and found to have a mean output of 9.5 watt. So we are supposed to formulate the hypothesis and check using z-test if mean output is consistent with the company's claim at 5% significance level. Given there are two values which are given, I will come to that later soon. Now here in this question, the idea of the decision making comes that company claims that there is some normal distribution for the power banks and the output mean output is 10 watt. A sample of those power banks, that sample is used to either accept the claim or reject the claim. So we are trying to do that and we are using the law of statistics because we know that X bar is supposed to be distributed normally for large enough samples and hence we can rely on the distribution of X bar to do this test. So what did we do next? We just tried to dissect the various portions. So let's just see what are the various portions we discussed. One is that the decision making is about one hypothesis being started with, and that is what we are calling as a claim. So here the hypothesis is about the population parameter mean. Remember the company's claim was that the mean output is 10 watt. Yeah. So we call that hypothesis with which we start as the null hypothesis, which we define as H naught, and we'll say that mu is equal to mu naught 10 watt. So that's the claim of the company. And then in the hypothesis testing, we also write down the alternate hypothesis, which we write as H1 or HA, and we call that this claim, whatever the claim was in the null hypothesis, is not true. So either the null hypothesis is accepted or rejected at the end of this analysis. So we should be clear what the null hypothesis is. Now, since the hypothesis is about the mean, so the best statistical evidence comes from X bar. Remember, this is what we did in central limit theorem also. That central limit theorem tells us that X bar for large and known sigma is distributed according to the normal distribution with mean mu and variance sigma square over n. What does that mean? That you can actually plot the distribution of X bar, which looks like a normal distribution. So in order to take care of point 1, we come up with statistical evidence-based analysis that we build X bar, or we say that there exists a parameter X bar whose value would be able to tell us whether this null hypothesis should be accepted or rejected. So X bar is going to be distributed, of course, normally. And then comes the third aspect of it. The third aspect tells us that we will test the hypothesis at certain level of significance. Remember, at the end of the question, it was given as the 5% level of significance. What does that mean? That in the whole normal distribution, we will make some critical regions such that if the X bar, which we are going to finally observe, lies in the middle of the distribution, then we will say that we accept the hypothesis, that is, this X bar is coming from a population parameter mu naught equal to 10 watt. However, if this X bar falls on left of mu minus Z alpha by 2 sigma over root n, and on the right of mu plus Z alpha by 2 sigma over root n, which is shown in the shaded region here, then we will say that we do not accept the hypothesis. We will not accept the claim, or in other words, we will say that we will reject the claim. So the whole idea of doing this decision making is on the basis of the distribution of X bar and assigning critical region. Now, when I am assigning the critical region, of course, I have come up with a word called Z alpha by 2. So in order to understand that, what we said that any normal variable which we know of X bar, for example, can be made related with the Z or the Z. So this is what we wrote. So Z is equal to X bar minus mu over sigma over root n. So when we are going to make any distribution with X bar there, I can convert that into Z variable as well, such that the alpha, the definition of the critical region, would be that probability that this Z variable lies between minus Z alpha by 2 and plus Z alpha by 2. Remember that Z alpha by 2 is some sort of a critical region. The points beyond which, if my X bar is found to be there, then we are going to reject the test or reject the null hypothesis. Not reject the test, but reject the null hypothesis. So this probability of minus Z alpha by 2 less than equal to Z alpha by 2, that is the middle region. This gives the probability of 1 minus alpha. And of course, you can write down the same thing as this. Mod of Z less than equal to Z alpha by 2 is equal to 1 minus alpha, or probability of mod Z greater than Z alpha by 2 is equal to alpha. Now, can somebody tell me why I am using Z alpha by 2 instead of Z alpha to say that this probability, those who were present in the yesterday's class, that I am using this Z alpha by 2 to give the probability alpha?
The area over both alpha by.
Sir, is it because of the symmetric behavior?
Right. So let me just again emphasize on that. So yeah, it is because of the symmetric behavior, and it is because of the area under the curve, the way you said it. So let's just try to understand the same thing again. Make sure that we discuss this and be clear about how to define it. So what we are saying is that we are arbitrarily drawing this. Arbitrarily drawing it in the sense that this is coming in from the question that at what level of significance you would like your test to be there. And we are making that. So please see that in the shaded region, if my X bar comes, I am going to reject that. Now, when I am writing alpha is equal to 0.05 or 5% level of significance, it means that the total area under the curve, under the shaded portion, that means minus infinity to minus z alpha by 2 plus z alpha by 2 to positive infinity, this comes out to be same as alpha or 0.05. So this is what we are saying when we are defining the level of significance. This is the value alpha which we give, that the total probability which lies in the shaded region, that is equal to this alpha. So our quest is to figure out this alpha. Yeah. Now we know, because of the symmetric nature of the Gaussian distribution, this portion has the probability alpha by 2 and this guy has the probability alpha by 2 for z to be symmetrically placed on both the sides, which means that this guy will have the area 0.025 and this guy also has the area 0.025, so that the total area under the curve, so this guy contributing 0.025 plus this guy contributing 0.025, so that the total area under the curve comes out to be 0.05. And hence what we are saying, this number minus z alpha by 2 is nothing but minus z 0.025 and this z as z 0.025. I am going to, of course, later call this something called two-tailed test, but this is not for now. It is just for the understanding at this point of time that when we are doing a test like this, what we are doing, that in order to make the total area 0.05, since the distribution is symmetric, we are trying to figure out minus z 0.025 or alpha by 2. So this is the reason why we are keeping this z alpha by 2, because in this test, the total area under the curve of the shaded region will be half of the area on both of the sides. So this is the reason why we have this. So once we understand this portion, then we are clear that we are going to find whatever the z observed is, compare that z observed with the values which are given, and if my z observed, which I will see from the values, is going to be less than minus z alpha by 2 or z observed is greater than z alpha by 2, am I going to accept the claim or am I going to reject the claim?
Reject.
So this means that I am going to reject the claim, reject the null hypothesis. This can be written, if you can think of, then I can also write down this mod z. Can you just tell me what will be the sign? I can write down the same thing in a simple way. Less than or greater than? Reject
Greater
H0.
than, sir.
Greater
This
than.
is greater than, and else if z observed mod is less than equal to z alpha by 2, then we will accept H0. Fine. So this is equivalent to saying that we are writing minus z alpha by 2 greater than equal to z. So this will be the criteria which we are going to put, that our central region is the acceptance of the null hypothesis and the side region or the shaded region is the rejection of the null hypothesis. This is why the test of, when I write the word level of significance, this word level of significance alpha, then this is associated with the definition of what we call as critical region. Because if the test falls, if the result will be such that z observation falls on left or the right sides, then we are going to reject the analysis or hypothesis. So rejection region, which I call as RR, and acceptance region. Once all of this is done, it is rather simple, because then we are just going to follow these steps in our problem. So this I call as acceptance region. Yeah. Now the same test, of course, can be understood maybe at some point better way. If you write down or X bar, so we know that X bar also follows this normal distribution. Basically Z we have built from that. So can somebody remind me what will be the critical region if I want to write down the same in terms of X bar? So let me draw the same plot again, but this time I am not going to have the Z variable. Instead, I am going to write down the X variable, which will be distributed about mu. And let's say there exists this shaded region. So can somebody tell me what is the point on the left hand side for the shaded region?
Mu minus sigma by root n.
Mu, no, it up to some point it is true, but you have to ensure that the area under the curve